what we're talking about today. But I found this quick little article of why we're going to talk about the conversions of degrees, minutes, and seconds. So, back in the Middle East, thousands of years ago, we used to think that there are 360 days in a year. That's how, in 360 days, there's 360 degrees in a circle. So, what they did was they used the circle in a way to tell time in a sense. Each degree represented a day. So then if you think about it, if I have something like 13.71, well, the 13 would represent the 13th day of that year. And that decimal point, that approximation after, would tell them the minute and the second of the day. They don't know why there's no hour, but if I have a decimal in a degree, I can rewrite it in this form of degrees, minutes, and seconds. So on the top of your page, we write degrees, minutes, and seconds. Degree is just the degree symbol. We write the minutes and seconds kind of like feet and inches. So the minutes is 1 prime, and then the seconds is a double prime. So here, if I have something given in degrees, minutes, and seconds, I need to think of it as a circle. Well, for minutes, if I'm given 1 minute, I know 1 minute here, there's 60 minutes in an hour, so it's 1/60th of an hour. If I'm trying to write this as a fraction to convert it into a decimal, and I would represent that as 1 with a little prime. That's all that means. For seconds, if I have quote unquote 47 seconds here, well, 1 second, I write that as 1 double prime, kind of like the inches in a sense. And I know that there are 60 seconds in 1 minute. So here, to get seconds, I'm going to take 1/60th of 1 minute, or 1 prime. Another way you can think about it is there are 3,600 seconds in an hour. So I also can say 1 second is the same thing as 1/3,600. So it's not as conventional to use this method because we know that there are 365 days in a year, but back in ancient time, they were able to use this process to figure out what time of the day it was, also the day of the year as well. So if I'm given something in degrees, minutes, and second mode, so given here, and I want to write it just in standard degrees, well, the first one, 64 degrees, that's just going to be our 64. 32 minutes, well, I know there's 32 minutes in 1 hour or a sense, or I have 1/60th of the degree. And then here, with 47 seconds, that is 47 over 3,600, or 3,600ths of a degree. Okay? So what I can do now is, if you have your calculator out, you can just go ahead and type this numerical value into your calculator to get the decimal approximation. I want to make sure everyone has their calculator out. You know how to enter this in. So I highly recommend putting in parentheses, like 64 plus, then in parentheses 32 divided by 60, plus, then in parentheses again 47 over 3,600. For these, 3 to 4 decimal places. Err on the side of caution, go 4. So what would be my degrees conversion? Alright, just type that in the calculator. Go ahead and approximate it to 4 decimal points. Go ahead, Charlie.
Oh, you said 4 decimal places?
if you were to take a protractor and measure that, that's the same thing as saying the 64th day of that year would be the 32nd minute, 47th second of that day. Okay. The only difference here with the negative sign, we're going to have to keep that out front so we can negate the whole entire quantity. So 408 degrees, we can leave that as 408. The next value, the 16 with the 1 prime, that represents the minutes. So I can write that as 16 over 60. And then the 20 seconds, that's the same thing as 20 over 3,600. That specific part of the circle. If I were to go ahead and put that in your calculator, I know it's going to be negative 408. Then go ahead and approximate to 4 decimal points. Anyone have it? 2722. So that's a very specific degree that they use to tell what time of day it was. Not very exciting. Don't use it as much anymore just because we know there's 365 days in a year. The next part's a little bit easier, going from degrees to degree, minute, and second, because actually the calculator will do this for you. So I'll show you real quick here. If I'm given something, I'm given 64.56 degrees. So I can go ahead, if I put this in the calculator, 64 point, what did I say, 56? 57 degrees? 56, okay. If you notice, there's this purple app button. If you read right above it, it says angle. So we're going to look at some kind of angle measurement. So if you hit that second and then angle, option 4 says DMS. That stands for degrees, minutes, and seconds. So if you hit option 4, it's going to take this 64.56 degrees and it's going to do the conversion for you. So that tells me that is 64 degrees, 33 minutes, and 36 seconds. So it does it for you. Did everyone find their angle button on their calculator? Yes. So we have 64 degrees, 33 minutes, 36 seconds. Go ahead and use your calculator for the next example. If I have 113.78 degrees, what would be the conversion with degrees, minutes, seconds? Type in the value into your calculator, hit the angle button, and it's number 4. Maya, 40 minutes and 48 seconds. Not too bad. The only other problem, if you want to write it underneath here, is if we're given something in, let's say, radians. So if I'm given something, I'm told I have 0.7, say, 865 radians. And my goal is to put it in degrees, minutes, and seconds. Well, the first thing says degrees. I'm going to have to convert my radians into degrees. What is the conversion to put something moving from radians into degrees. Yeah, I can change this to degrees first, so I can use my calculator. I can multiply by 180 over pi. So if I were to go ahead and convert this to degrees, I get approximately 45.06 degrees. Do decimal places. If you do 3, that's fine as well. Now I can go ahead and convert this to degrees, minutes, and seconds. If I were to put in 45.06, go to the angle button, hit number 4. What would be this in DMS? Go ahead, Maya. 3 minutes and 36 seconds. That might change a little bit depending on how many decimal places you go out. But just the idea of being able to convert and represent things, like I said, we have radians, we have degrees, minutes, and seconds. They're all just different ways to measure angles. Are any questions? So tomorrow, there is book work. I will check that. 4 people to present tomorrow. Have any volunteers? Dave, number 18. Stephen, number 24. Christian, number 71. And Ian, number 77. Okay. So I'll check book work tomorrow, and that you have your special right triangle. The first 2 pages should be done for tomorrow. We're going to go over the Chapter 8 test as well. So if you want to pull that out, if you didn't do your corrections already, I have a couple of yours from this class. Also, if you feel like you could have done better on your Chapter 8 tests, I'll give this class, I talked to some of you already about retaking it tomorrow. I have a list of a couple of you that I feel like you could do better. So if you want to come talk to me, we can schedule a time to make up the test. Try to improve your score a little bit, okay? So you don't have to raise your hand or anything. You can come talk to me after class. I'd be happy to let you retake it, okay? So on the top, number 1 and 3 were good. 2, there was just a couple issues with making, I got a couple 4/9s, but other than that, nothing too serious. The biggest issue with number 4 was that people went a little too simplify crazy. So when you factor that numerator as perfect squares, you could factor your denominator using AC grouping. Right off the bat, x plus 2y over x plus 2y, that simplifies. But some people said this was also the additive inverse. If it was x minus 2y over 2y minus x, yes, that would be the additive inverse. But the variables also switched as well, so that would not be the additive inverse. Please, the only thing I ask is just don't frantically copy down the answer. If you have a question, like I said, if I want you to just frantically copy down the right answer, there would be no point in corrections. So understand what you did wrong and how to make the correction. 5 and 6, I don't think we had any issues there. Some of you for number 6 gave me the GCF. The LCD was just what would be the common denominator. Okay. Number 7, pretty well, factoring, canceling out common terms. I don't think there was any major issues there. Number 8, the only big issue there was, once you multiply by the reciprocal, to factor 7 plus 8y plus y squared, you can rewrite that as y squared plus 8y plus 7. So once you factor that, you'll get y plus 7 times y plus 1. Yes, Charlie. Yep. But again, please just don't frantically copy it down. Understand what the problem is being asked. So I have this 7 plus y and y plus 7 cancel. Order doesn't matter when we add, so we can cancel those. Same thing with the y plus 1 and 1 plus y. Those will cancel. I have a y and a y that will also cancel. So that would be 7 over 1 minus y would be my final answer. Again, a couple of you tried to I don't even know what you try to do here. 1 minus y squared. That's just 1 minus y, 1 plus y. It's a perfect square. Anything on the front page? Number 9, the biggest mistake there was you subtracted, but you could also factor out a 2 from your numerator. When you do that, you get 4x minus 1 over 4x minus 1, which will simplify to 2. Number 10, I accepted a couple different answers depending on how you use the additive inverse. The big thing there is I needed to see that you could use the additive inverse. It was 2 points, so if you incorrectly used the additive inverse, even though it's just a minus sign, I needed to see that you could use that process. So I took off a point there. Number 11, biggest mistake is that some people try to factor that final answer in that numerator. We can't factor negative 12. That adds to 13. We couldn't use AC grouping. So it wouldn't be like whole numbers when we factor. For number 12, the biggest mistake was once you found your GCF, which was x plus 4 times x plus 3 times x plus 2. Once you do that, you had to distribute this negative. So if you were to go ahead and FOIL this, and then you had to distribute that negative to all 3 terms. That would have affected how your final answer would have simplified. And the last thing on that page, number 13, your LCD was x minus 4 times x plus 4. Again, making the common denominators, but remembering to distribute that negative through. So you'll get some things that cancel. That one actually worked out really nice, where once you subtracted with your numerator, you're left with 8x minus 32. You can pull out a common factor of 8. And when you do that, you'll notice your x minus 4 and x minus 4 will cancel. So the final answer would be 8 over x plus 4. Anything on this second page that you would like to talk about? Last page overall went pretty well. Number 14, we didn't need to make common denominators or anything. You can write it as a division problem, multiply by the reciprocal, and just see what cancels there. Final answer would be 6x squared over y squared. And then in number 15, your LCD of your primary numerator is x squared y squared, and your LCD of your primary denominator is xy. So when you add, or when you subtract your primary numerator, you get x squared minus 9x squared, y squared minus 9x squared, and then you're going to divide by y minus 3 all over xy. Multiply by the reciprocal. Some of you got to this point, but it could simplify more. You can factor, we have perfect squares. Your xy over x squared, y squared also simplifies as well. Final answer is y plus 3x all over xy. Corrections are still due on Tuesday. If you would like to retake, please come see me. I won't find you, but I'd be happy to walk you through anything else.